Today we're going to start our unit on graph theory, and today we're mostly going to talk about some introductory vocabulary. We're going to talk about why graph theory, where do we use it, how is it useful for today, and then after that we'll get into specifics about graphs, how do you draw a graph, and different parts of graphs, and different things that you can find within a graph. So let's first start by talking about why graph theory. So graph theory is important today because it's important today to be able to plan efficient routes. So examples could be something like a FedEx truck has a certain number of deliveries that he has to make, and he has a set of houses that he needs to go to, and in order to figure out what's the most efficient route for him to go, you can use a graph in order to simplify the problem and be able to come up with an efficient route. So that's an example. Another example could be laying fiber optic lines for internet in a neighborhood. If there are certain homes which have which want the fiber optic internet, what's the best way of laying those out in order to most efficiently get it to customers, but at the same time not spending as much as you actually need. So here's a particular example. So this is a part of Dedham, right near the high school. And let's say there's a lawn inspector, and he has to walk down every street to make sure that the landscaping meets code. Now, this lawn inspector, he wants to be able to do this the most efficient way possible. He doesn't want to have to backtrack and walk the same road twice. So, in order for him to do this, one way of coming up with a more simplified version of this map is to use a graph. And so what you can do is you can use dots and lines to represent, well, he has to hit certain homes, and the lines can represent the path that he's going to take, and the path that he's going to take can take him to certain houses along the way that he can see as he goes along that path. So by coming up with these dots, so these points, so most of them you'll see are at corners or at the ends of roads or where there's a turn, and then connecting them with lines, we can simplify this problem, and this lawn inspector will be able to come up with an efficient route in order to be able to minimize the amount of time that he needs to take in order to look at all the lawns. Okay, so let's talk about how we define a graph in this realm of graph theory. So a graph consists of a set of dots, which are called vertices, and a set of edges, which connect pairs of vertices. Okay, so vertices and edges, those are the two main things that you'll see in one of these graphs. And graphs are equivalent if they have the same edge connections between the same vertices. So over here on the left, here's an example of a graph. So all the dots are vertices, all the lines between the vertices are edges. Now, a graph can look different, but we can still say it's equivalent as long as you still have all those vertices, and all those vertices are still connected to the same vertices. They're the same edge connections. So for example, this, I know it looks slightly different than the one on the left, but these are actually equivalent graphs. And you'll notice we still have all 6 of those vertices. And the edge connections, it's not just that there are the same number of edge connections, but that you can map each vertex to its corresponding vertex on that second graph by which vertices it's connected to. So for example, on the left graph, the vertex that's on the bottom there, kind of hanging out there by itself, is just connected by one edge. And you can find that on the second graph, on the far left, on the second graph, right, there's that one vertex that's sitting there kind of almost by itself, but it's connected just by that one edge. So we can say, well, that vertex corresponds to that vertex. And you can find all those matching parts, and we can say that those graphs are equivalent because they have the same vertices and the vertices are connected in the same way. Okay, so in this first example, it says, the city of Königsberg was set on both sides of a river and included 2 large islands which were connected to each other or to the 2 mainland portions of the city by 7 bridges as shown below. Okay, simplify the picture below using a graph. Okay, so just so it's clear, the blue parts there, that's definitely the water, that's the river, okay? And it says this includes 2 large islands. So the landmass that's right in the center there, that's one of the islands. The landmass that is almost completely surrounded, it's just cut off in the picture. That second one on the right, that's going to be the second large island. Okay, so those are the 2 large islands. So it says the city was set on both sides of a river and included 2 large islands. So those are part of the city, which were connected to each other, or to the 2 mainland portions of the city by 7 bridges. Okay, so the rest of this picture here is also part of the city, and the whole city is connected to these 2 land masses, the 2 large islands, by these bridges, which are shown in green. Okay, so simplify the picture below using a graph. So what we're going to do is we are going to let each landmass be represented by a point. Okay, so we clearly have 4 land masses, right? So 1, 2, 3, 4, right? Those are the 4 parts of the city that you can be in. And then we are going to let each bridge be represented by an edge, right? So that's, you can think of that as a path to that part of the city. So for example, there are 2 bridges to get from the middle island to the north part of the city. There are 2 bridges. There are 2 ways to get there. That's fine. So you'll draw 2 edges going from that vertex to the one up north. We'll do the same thing as we look down and we see from the middle island to the south part of the city. There are also 2 bridges that take you there, so we'll again draw 2 edges there. And we do the same thing with all the bridges. Okay, so that gives us this. So when we draw graphs, you don't necessarily have to draw straight lines. Okay, the important thing is that it's clear from which point to which point that edge connects. It doesn't matter if it's a straight line, it doesn't matter if it's curved. Try not to make it both straight and curved. That way it can get confusing. You might think that there is an extra point in there, so just try to make it smooth, but it can't be a straight line and smooth. It could be a curve and smooth. But generally, as long as it's clear where that edge is connecting from one to the other vertex, it's clear which 2 vertices it connects, then you're good. So that's all this example is asking for, just to simplify the picture using a graph. So this particular example is actually quite a famous one, and it's known as the 7 Bridges of Königsberg. The particular problem that this is, so we've kind of simplified the problem, but the problem itself was to determine if there was a way to walk through the city and cross each bridge once and only once. So that's the problem there. Now there's a well-known 18th century mathematician whose name is Euler. It looks like Euler, but it's Euler. And he was able to prove that this problem actually had no solution. And we will talk more in depth as we get along in this unit about how we can figure out if there is a way to, for example, cross each bridge, which in this case is an edge, how to go through each edge only once and not repeat any. So we'll go more in depth later on. So a couple more formal definitions. So a vertex is a point in the graph where edges meet. Note that vertices only occur when a dot is explicitly placed, not whenever two edges cross. So sometimes it might not be possible for you to draw your graph without letting edges cross, which is fine, but when those edges cross, it does not create a vertex. Okay, so you have to be very clear where those vertices are when you're drawing, and just make sure that you draw a very, very clear dot. All right, an edge is a line segment connecting pairs of vertices. And then a loop, which we haven't talked about yet, but a loop is an edge that connects a vertex to itself. So a loop is technically a type of edge, okay? But in particular, it's when a vertex is connected to itself. Okay, so here's a picture. So all those very clear dots, explicitly drawn in dots, are vertices. And then anything that connects from one vertex to another is going to be an edge, including what we have there on the right, which is a particular type of edge called a loop. Okay, so you can say this graph has 3 vertices, it has 3 edges, and one of those edges is a loop. Okay, a couple more formal definitions. So a degree of a vertex means the total number of edges that meet at that vertex. Okay, the total number of edges that meet at that vertex. Okay, now note that a vertex with a loop would count as degree 2, right? Because the loop goes from the vertex back to itself, so there are technically 2 lines that come out from it. Okay. So just so we can see this, if you have a vertex and there are no edges coming from it, we would say that it has degree 0. If it just has 1, degree 1. If it has 2 edges coming out of it, degree 2. 3 edges, degree 3. Okay, and then we would say that 2 vertices are adjacent if they are connected by an edge. So not that somehow you can get to the other one, but that there's just one edge connecting those 2 vertices. Path is a connected sequence of edges that shows a route on the graph. Okay, a connected sequence of edges that shows a route on the graph. Now, each edge is used at most once, so there are no repeats. And then the second thing is what we call a circuit, which is a type of path. And in particular, it's a path that begins and ends at the same vertex. So every circuit is a path, but not every path is a circuit, right? A circuit is a type of path. So a path is just going from going through a sequence of edges, just as long as there are no repeats. And a circuit is a path, so again, a sequence of edges, but it's one where it begins and ends at the same vertex. Okay, so for example, we have this graph here. We'll label all the vertices. So if you were asked to find a path from A to F, well, there are many paths to get from A to F, right? So as long as you're using each edge only once, no more than once. You don't have to use the edge if you don't need to, but you can't use an edge more than once. So for example, it could be A, B, D, F, right? That would take you to F. You could go A, then C, then F. That can take you there too. A, C, D, F could also do that. And A, B, D, C, F could also do that. Okay, so those are all examples of paths that go from A to F. Now, what if we were asked to find a circuit? Let's say the circuit starts and ends at A. So one example could be A, C, D, B, A. Okay. You could go through F as well. A, C, F, D, B, A. That works. A, B, D, C, A. So going the other way. Or A, B, D, F, C, A. Those all work. So those are all examples of paths. So where you don't use an edge more than once, and you start and end at the same point. And then two more things to go over here. So when we talk about graphs, we say that a graph is connected if there is a path from any vertex to any other vertex. Okay, a graph is connected if there is a path from any vertex to any other vertex. On the other hand, we would say a graph is disconnected if there isn't such a path. So if there's no way to get from a specific vertex to another vertex within that graph, if there's no path, there's no way of getting there, then we say it's disconnected. So for example, in this first one, we would say this is connected because if you pick any 2 points or any 2 vertices, you will be able to find a path, right? So say you wanted to get from B to E, right? There is a way to get there, B, A, C, D, E, yep. Okay, pick another 2 from A to F, right? A, C, D, F, right? There's a path, there is some way to get from one vertex to another. So we would say that's connected. On the other hand, in this particular one, we would say this graph is disconnected because we can't get from B to E, right? Whereas there was a way to get from B to E in the other graph. And hopefully you can see pretty clearly that these are disconnected. You can, without taking out any edges, you're able to kind of take apart the graph into 2 parts, right? So if you're able to, they're disconnected, which means you can kind of pull up that first part with BACF, you could pull that up, and the D and the E, you could pull that down, and they would be 2 very separate graphs, right? So in that case, we would say that they are disconnected.